Hi, I'm DJ Ware. On this episode of the CyberGizmo, I'm going to be looking at the performance of Linux on bare metal versus the performance of Linux on virtual machines. Stay tuned right after this. As many of you know, I use virtual machines when I'm testing my distros. It has mostly to do with just limits in the amount of hardware I have in order to dedicate. So most of it right now is my ZFS is still under test, and that is the normal one I use for testing on hardware. I prefer to test on bare metal, but at the moment I'm just not able to do that. So I have been testing more on virtual machines. And so that generates some comments from some of my viewers, like this one that says, they can't understand why I use virtual machines when bare metal is so much better for Linux. Or, I'd rather see these videos on bare metal, but they don't really explain why. Or, virtual machines are not credible for comparing systems, which is kind of a puzzling one. But, so, you know, I could just sit by and just try to guess on something as to what some of these things might be and where some of the problems might be with virtual machines versus bare metal. But the first question that always comes to mind are the assertions true, and what are they really getting at? Is bare metal really better than virtual machines, and is there a performance difference that is significant between bare metal and virtual machines? So I thought, as usual, I'll take an engineering approach and try to answer it versus, you know, just trying to say, well, I think it's this. I don't think that matters. I think what we need to do is empirically look at it and see what is the ground truth here. So some of the things that are common, and if you read articles about bare metal versus virtual machines, some very common things that always come up is direct access to disk, memory, and CPU make the performance kings for bare metal. And my question is that really true? Is that really right? And then you'll see them say things like abstract disk, memory, and CPU come with a performance penalty. But is that really true as well? That's what I hope to try to discover today in trying to delve into that. But let's look at some of the pros and cons between bare metal and virtual machines. So for bare metal machines, they are good for data-intensive workloads. There's no question about it. I remember a couple of times in the past where we had database servers that we attempted to virtualize, and the performance, now this was a traditional SQL database, so it was an Oracle database. And we tried to virtualize them, and oh my God, the performance was awful. It was absolutely terrible. Now this was back probably around the 2005, 2006 timeframe, and Linux still had a ways to go with SMP development. So, yeah, it just wasn't pretty. It wasn't pretty at all. And there was a lot of work that was still being done in the virtual machine space as well. The second thing about bare metal is you have access to the full server. You don't run into if you're running in a cloud environment that's multi-tenant, you might have a noisy neighbor that is consuming all the processing capability of the machine, and you're not getting very many cycles, and so your performance on a virtual machine might be worse. So bare metal obviously doesn't have that problem. The third thing is that you do get consistent performance on bare metal, and the containers don't need to run in a VM because containers can run directly against the hardware. In virtual machines, they're good for high variability workloads. In other words, I may have a number of virtualized machines that require different numbers of CPUs, different amounts of memory, different amount of disk, and I can easily accommodate those in a virtual machine. So I can break up and utilize the parts of the hardware that I need for that machine without dedicating the entire hardware platform to those applications. Virtual machines I definitely can spin up a lot faster than I can a bare metal. There's also more modern, I'm not going to say better, but it's more modern management software for virtual machines. It's just because the time has gone into those. A lot of the tools that you have on bare metal haven't really changed much in 25 years. And they're still the tools that work well on bare metal, but they don't really offer you much beyond what they offered 25 years ago. Whereas in the virtual machine market, those tools and things have evolved over time, and a lot of them are very good for doing backup and doing testing. It's also less expensive to host virtual machine platforms because you're not absorbing the entire cost of the hardware. You're only using a portion of it. There's a variety of virtual machine sizes, and that allows you to fit the application load to the size of the virtual machine that you need for that particular app, which again, it does several things for you in the ability to utilize that hardware better. The cons for bare metal is obviously it's more expensive because if you're following the mantra of Bell Labs, one app per server, then you are, in today's market, you're wasting a lot of resources. I mean, all these machines today are all multiple core, they're multiple CPU. They have the ability to hold massive amounts of memory and massive amounts of disk. So you're not as agile. It takes longer to spin them up. And I can tell you a story that we originally, in the last project that I worked on for Raytheon, we had bare metal servers because we felt at the time that those were going to offer the best way of being able to get the performance out of the hardware that we needed in order to handle the imagery that was coming down from the U2. So yeah, that's a pile. It's huge. And so it took longer to set those machines up, usually about 3 weeks in total. There was a total of about 100 machines in the mix, and it took about 3 to 4 weeks to stand those all up. It was just each machine had a different piece of the application software, and so you couldn't just cookie cutter. You couldn't use a jump server very effectively, other than maybe lay down the initial operating system, because the jump server wouldn't really buy us anything in setting up the types of servers that we had to bring up. So yeah, it just took longer, and that's just the way it was. But the management tools for bare metal systems are just not as advanced. Like I said, they're 25 years old. They haven't changed a whole lot in the time that those were developed. And then capacity is usually too much for most workloads. So there's so much spare capacity on these bare metal machines today, and that is getting worse. So that's one thing that managers don't like to see. They don't like to see the hardware that they've purchased sit idle. And then there's SMP, but I don't think I'm ready to quite talk about that just yet. The symmetrical multiprocessing is what we're talking about there. And virtual machines, the cons are, yeah, there's a potential for the noisy neighbor, especially if I'm multi-tenant. If I'm controlling the application load and on a virtual machine, then I have some means in order to manage that. But if I'm in multi-tenant, I may not. There is inconsistent performance. Again, it depends on the workload that the machine is working on in addition to my virtual machine, because essentially you're sharing the resources, but that's, I would contend that that's no different than on a bare metal machine. If you were to host multiple apps, you would have the same problem. But there are some ways that you can manage the inconsistent performance, and those have to do with the VM software that allows you to move the virtual machine itself to another piece of hardware that is less busy. So shared resource security concerns, yeah, there's always security concerns when you have resources that are being shared. I remember when we attempted to put up Blade servers that had a network mezzanine, we found ways that we could poke holes through the network to gain access to the other virtual machines. And so, yeah, not good. So there are those concerns, and you do have to watch out for that. That, however, was not an issue with bare metal that was racked, the traditional rackable servers. So it was only in the shared mezzanine that we saw those kind of issues. But yeah, there's always shared resource security concerns. So let's look at SMP for just a second here. Now, this Core i7-8750H is a 6-core, and it has 12 CPUs because of hyperthreading. So this divergence is going to be somewhat aggravated by the fact that it's using hyperthreading for the CPUs beyond 6. But I would point out that the divergence in performance between my measured and my expected results. Now, what I expect is that as I add CPUs, my performance doubles for 2, triples for 3, quadruples for 4. But you can see that there's already a divergence at 4 cores here, and it is growing worse up until the maximum of the real cores up at 6. And then it just sort of continues along that trend line for 7, 8, and 9. And then there's a dip again at 10, and then it really accelerates at 11 and 12. So you can see there's a huge difference here between what I would expect to see and what I'm getting with SMP. And that is because SMP is expensive. Now that's the symmetrical multiprocessing is how I control handling multiple loads, multiple applications on bare metal, and offers up some degree of parallelization. But SMP is pretty heavyweight. It has an arbitrator that sits up at the top that manages the cache between all of the CPUs. The more CPUs you have, the harder, the more work the arbiter has to do in order to make sure that the cache remains coherent between all the different applications that's running, that pages don't get cycled out of memory, especially data pages don't get cycled out of memory that are still in use by other processors. So yeah, one processor may mark a page for, hey, you can remove this, I'm done with it. But another CPU may be using that, maybe sharing that same code base. So that it is shared memory in SMP, and so you see some of this aggravation going on. Same thing is in the more later processors. Now I know these are mobile, but the only difference between mobile and desktop is that you see things sooner in mobile because the limits of the CPU. But desktop and also server platforms, they're all going to exhibit this with SMP over time. It's just the point where the divergence occurs may be different. So in this case, you see it sort of stays pretty good up until the maximum of the 6 cores. And that's also a 6-core machine and has 12 cores with hyperthreading turned on. So yeah, you really see the divergence really sharply occurring as soon as hyperthreading kicks in and being used. So yeah, so my measured and expected results are not staying in tune. I would be interested to, I don't have any larger machines than this. These are the largest machines I have at present. I'm still trying to get one of the new processors with more cores to see what happens, but so far that's the only thing I can deal with here. So these are my results. You might want to look at yours and see what you're getting. Let's look at a comparison between bare metal and virtual machines. This benchmark has been around since it's been modified and changed and enhanced since I think the late 80s. The last iteration of this was 10 years ago, where they brought it up into supporting the modern kernels of Linux. So this is running on a Core i7 6700K. This is the largest desktop machine I have. It has the most disk. It has the fastest disk on it. It has about 32 gig of memory, and of course it's a 4-core 6700K, of course. So the way I ran this is Ubuntu 2004.1 LTS on both the bare metal, and then I ran KVM through Werq Manager on top of that same bare metal platform to get the virtualized result. So I wasn't running anything while I was running the benchmarks on the bare metal, and then I brought up the virtual machine and reran those same benchmarks again. It takes quite a bit of time to run. So then I just totaled them all up together, because I want to look at this as an aggregate, because workloads occur in aggregate. You don't just do syscalls without doing any process creation. You don't just do pipe switching without some kind of data movement in the system. So the workloads always come together, and so I wanted to measure these together to kind of simulate what a typical application might be doing. So hopefully you agree with the tenet of that, and if you do, great, and if you don't, well, then you'll need to measure it the way you want to see it. So there's only about 0.88% difference between the bare metal and the VM. So there's nothing conclusive here that you can really walk away with other than maybe there's some noise. Some things performed better. Some of the benchmark tests, that the individual tests performed better on the virtual machine. Some of them performed better on the bare metal. So yeah, but if you look at it in aggregate, it's about the same. They're very close in the performance. So I wanted to look at a little bit more of it. So I took some individual tests and then did this one. This is events per second. This is intervals looking at CPU cycles. So this is trying to load the CPU up with a lot of events to run, and I get some numbers that are 2760 on average for the virtual machine and 2778 on the bare metal. Now there is a difference there, but is that huge? No, not really. It's the difference between those is very slight. And if you look at some of the intervals, some of them are far apart, some of them are closer together. So yeah, there might be a little bit of more overhead in virtual machines on the CPU side of things than there are in bare metal. But is it huge? No, it isn't huge. This one is really looking at threading and how well threads are managed on the machines. And that would be SMT. So that's the other half of the performance curve for most of the Linux operating systems. And as you can see, the virtual machines are walking away with it. I mean, they definitely handle threads a lot better than bare metal does. So yeah, and it's mainly because you're dividing up the CPUs and making things easier, which is virtual machines were really meant to soak up the cycles of bare metal. As the machines became larger, there was more and more idle time on those boxes, and virtual machines are really meant to soak that up. This one is memory events, and there's one interval where the memory events are faster on the virtual machine, and two where virtual machine is slower than bare metal. So it's mixed results there. I suppose, I ran it 3 times. I suppose if I ran it 20 times, I probably would still see mixed results between the two. I don't know if it's 2 to 1 like it is here, where bare metal seems to perform better than virtual machines, but clearly it is not a huge difference considering the number of events that are being handled here. It is not a huge difference if you look at it. Now, yeah, if you look at the bar graph, it looks, oh my God, it's really huge, but it's not. The next thing I looked at was network performance, and I'm using iPerf3 to do this. I sent the packets out over the bare metal to another machine that's on the network, and also tested it inside the virtual machine doing exactly the same thing. And the results were not really surprising to me. I know that in a lot of cases, KVM does a pretty good job of handling hardware because it is part of the Linux kernel, and so it doesn't have to spill out into the user space in order to emulate and be able to attach itself to the network hardware directly. So it does pretty good on hardware emulation for the most part. And as you can see here, with except for interval 4 there, the virtual machines were faster. And I don't know what was going on at interval 4. My network carries more traffic than just benchmarks, and I can't shut down a lot of it. So it could be just network load picked up for a minute, but I don't know. But anyway, there were times where that workload changed over and bare metal was faster. And I suspect that would be true, of most things, that you will see that there are times when bare metal is going to be quicker and times where virtual machines are be quicker. That's because they run pretty close neck and neck in the ability to handle workloads. So what about the I/O zone tests? So I ran those too, and these are the read tests. Bare metal versus raw reads, virtual machines definitely faster. So we don't have, I've heard this argument several times from people that virtual machines are slower in I/O because they're using user space in order to conduct the I/O to the machines. No, not with KVM. No, it doesn't do that. As you can see, it clearly doesn't do that. Also, fread, which is of course, the C reads that you would more commonly. That's the API for C. that's pretty evenly matched. There's a little difference, but I wouldn't say that at bare metal or virtual machine is a clear winner there. I'd say they're about the same. In P reads, there's a slight an advantage to bare metal when you're running in lower workloads, but it's not, again, it's not a huge difference. And then as you ratchet up, virtual machines do quite well. Let's look at writes. A little bit different story over here on the bare metal using F writes. There is clearly a difference between bare metal and virtual machines, and it is about 2 to 1. So yes, bare metal is faster on writes than the virtual machines are. In my case, this is going to a Samsung 970 EVO 1 terabyte. So I don't know if that's some kind of issue with the ability of the virtual machine to handle writes going through PCIe, because you are using the PCIe bus or not. But clearly, yes, bare metal is faster. So P writes, again, we see that the first working load is a little lower on the virtual machines, but second, third, and fourth are a little faster, and the fifth we fall back again a little bit. Bare metal on initial write, I would say, except for the first worker, they are pretty even. I mean, there is some, there's some advantage, a slight advantage maybe to virtual machines, but not, I wouldn't call that telling. It's probably in the noise, but you can see that virtual machines definitely does not, within a single virtual machine, does not handle workloads very well. Now, I had restricted that to 2 cores, so. And I also restricted all my benchmarks to 2 cores in the bare metal, mainly because I wanted to make sure that I was comparing apples to apples and wasn't giving one an unfair advantage over the other. So, bare metal relies on symmetrical multiprocessing for parallelization. That's been around with us since true SMP has only been around since the early 60s. That's kind of gone in and out of favor over time. There are problems with it, particularly as you get up into the more complex workloads. The limitations that you usually run into is the coherent cache problem. There's also the problem of if a application that is running across multiple cores, Apache might be an example of that, where it would be running across multiple cores, and if one of those cores gets a page fault that goes out early and the arbiter isn't, because of the time, there's race conditions that can occur in SMP, and if it doesn't catch it in time, you could cause a failure on that particular node. And those cascade because Apache is relying on information coming back to give status, and eventually the entire app will crash. So that is not uncommon. It doesn't, I mean, I wouldn't say it happens all the time. And more likely you'll run into the coherent cache problem, and that will cause performance issues as you move up, as you've seen the divergence. We've seen that. SMP in 2.0 used to use the big lock mechanism, and so it was pretty terrible. I remember that back in those days we would see. Now, I was doing SMP on Unix at the time, which used a similar kind of strategy, a big lock. And we would see 50% degradation in performance going from one processor to the second. So instead of getting the expected 2 times the performance, we would only see 1.5 times the performance of the machine. And the odd thing is, when you added the third one, you got another 50% hit on top of that. And so the third processor would only add 25% more performance. And then the fourth one only 12.5% more performance. So as you can see, SMP diminished off pretty darn fast. So that is not true anymore. The 2.6 allowed the load balancing across the CPUs. It also added a number of performance improvements that made SMP a lot better. So what we had determined back in, I think, around 2006 or 7 was seemed to be this diminishing returns that occurred at 8 core. And I'm going to jump to the bottom of the slide for a second and talk about that. So I watch there's a gamers channel that they build hardware for gaming, and then they review new products, and they're really good. These guys are really, really good. And they were looking at the AMD Ryzen 7 5800X, as well as some of the others, the 59 and so forth. And they said that the sweet spot for gaming on the AMD platform was the 5800X. Well, I almost choked because that's an 8-core processor. So is that because of the SMP thing? Because Windows also does SMP as well. So is that because of that? I just thought that was kind of coincidental that they picked the 8-core as a sweet spot. And their benchmarks showed that they didn't really get the performance gains from the 12-core, and they saw diminishing gains from the 16. Now, if they're running multiple workloads, like, if you're recording the video and streaming it, yeah, there would be some advantage to that. So what about gaming? Doesn't that run faster on bare metal? Well, yeah and no. I mean, you're going to see the same things that I saw in the benchmarks in between that, but there are some advantages to running gaming in a virtual machine. The first thing you need to realize is that most of the games, and now there are a few that are CPU heavy, but most of them are GPU heavy. So if I'm dedicating the GPU hardware by passing it through to the virtual machine, then it has full control over that GPU anyway. And so the performance gains or the performance loss from using a virtual machine should be mitigated by the fact that I'm using the real hardware. So, yeah, I mean, there are GPUs that are very expensive that you can divide up and you can part out those to share them among multiple users. But most of the home gaming GPUs can't do that. So you either dedicate the whole processor or you don't. And they don't, like I said, it just doesn't heavily tax the CPU in most instances. Now, you might tax the drives on occasion because you're loading in a new scene, or you might tax the network if you're playing in a multiplayer game. So, yeah. Finally, so does it matter if it's bare metal or virtual machines? Well, the answer is always, for me, is going to be it depends on your workload. Depends on what you're trying to accomplish. Like I said, when we had databases and we were trying to virtualize them, that was really a poor choice. But if you're looking to try to utilize as much of the bare metal hardware as you can without wasting it, and we don't want to waste it, because what you end up having to do is that you end up having to spend more money on servers that aren't being utilized. Well, that business model isn't going to last very long in most corporations, and it shouldn't last very long for you at home either. Having to have multiple machines to do things. I've seen quite a few gamers that are using multiple machines when they're using Twitch to stream. And the reason they do that is because they don't want the overhead on the machine that's being used for the game, or they just don't have the resources on that machine to be able to do both activities at once. So the reason I use a VM is to show the differences between distributions. I'm not benchmarking them. I'm just talking about here's some of the features and here's some of the things. I do prefer to use hardware, but in all honesty, if you're expecting me to do it on bare metal because you think that that's somehow going to show you how it's going to run on your machine, I'm afraid you're sadly mistaken. My hardware isn't the same as yours. And so it'd be very difficult for me to come up with a perfect match for every person that's watching a video on bare metal and say, you can be assured that this is going to run just like this on your machine, because you can't. You may run into issues with your hardware because the drivers don't support it. You may run into issues with maybe some of the drivers are faulty or buggy and that you're using. Maybe you have a different network card that I'm using. Maybe your memory is different. Maybe your CPU is different. So there's probably 1,000 different ways to try to match up hardware, and there's nobody that's going to be able to do that. On the other side of it, with KBM, at least, most of the processing is done inside the kernel space. And so that's why you see efficiencies. Not all of it, but most of it is. There is one other type of virtual machine I haven't covered here, which is para-virtualized virtual machines. And those are typically Xen-based or XFCP-NG. I have not done an analysis of that. If you want to see that, let me know in a comment below. And maybe I'll look into that. I could run it and try it. Now, Proxmox is KVM based. Virt Manager is KVM based, of course, and Gnome Boxes is KVM based. So, and there's a number of them that are as well. I did not also test VirtualBox because VirtualBox is a different architecture, and I have run into performance problems with it in the past, so I know there are performance problems with VirtualBox, and I don't recommend it. So anyway, that's what I had for today. Hope you enjoyed this, and if you did, please like and subscribe. Hope to see you again real soon, and bye for now.